Great. All right, you get a prize. I think you need a hat. Good afternoon, and welcome back to the Extraordinary Technology Conference 2017. Today I get to introduce you to a conference staple. William Alek is the president and CEO of Aurora Tech. Aurora Tech is dedicated to bringing forth and advancing exotic free energy self-sustaining technologies for the world. William is the inventor of the Smart Pack, the SZT, Free Energy Overunity Management Systems. William has more than 30 years of experience as an embedded computer hardware, electronic hardware, and software engineering consultant, and has a BSEE degree from ITT in Chicago, Illinois. I'd like you all to give a warm welcome to William Alek.
Thank you, Vernon. Yeah, I'd like to thank Steve Elswick for giving me this opportunity to speak to you today. Yes, the physics of free energy over unity transformers. I've been, in this field since the late 90s, and how I got interested in it was attending a Tom Bearden conference. Of course, Tom Bearden's he's quite an extraordinary speaker, and he spoke about this extraordinary device called the Floyd Sweet device, which he personally eyewitnessed. And what's so amazing about the Floyd Sweet device is that it had a power gain, energy gain of about 1,000,000 to 1. And what his transformer did, you put a milliwatt of power in and you get a kilowatt out. And that concept really caught my interest. And so I've been pursuing this activity since the late 90s. So let's get started here. All right, what I call the Bible, and this is a must-read document. It was published back in 2002. It was written by Don Hodson. The guy is absolutely brilliant in how he presented this material here. And it has to do with the Dirac equation and what he presented as the sea of negative energy. Now, the Dirac equation was published back in 1928, and it caused a huge firestorm in the mainstream science community. And the issue there is that the Dirac equation predicts that E equals plus or minus mc squared. It wasn't just E equals mc squared. It's plus or minus mc squared, and that's how the equations worked. And these equations, they knew about the electron back then, back in 1920s. They didn't know about the positron, but his equation predicted the positron. And then he also predicted the negative energy version of the electron and the positron, okay? And so this article here, again, just a brilliant piece of information, because really all my technology that I'm going to be presenting to you today really comes out of this article. You can find virtually everything in this article. Okay, so what's in it? Well, he forms a theoretical basis for devices that utilize this negative energy component. And of course, back in the 1930s, all the great physicists back then took out the negative energy portion of this. They just didn't want to deal with negative energy. They wanted to deal with only real space, because negative energy can only be found in this complex domain. You have to work with complex algebra in order to access this negative energy component. And they just didn't want to deal with that. They wanted to keep it nice and simple, just deal with the real universe. And that's what we have today. All our devices work on real energy, real positive energy. Okay, so his solution, the Dirac solution, E equals plus or minus mc squared. So you can have a positive electron, positive energy electron, or a negative energy electron. It can have positive mass or negative mass. Okay, so it was first introduced, E equals mc squared, was first introduced back in 1890 by Oliver Heaviside. Dirac came along and introduced this plus or minus sign, okay, in the equation. And so there's a boundary between this positive and negative energy, and today we call that 0 point energy, absolute zero. And that marks the demarcation between positive energy and negative energy, okay? And so what you see here in this picture is that for positive energy can only exist in real 3D space. That's our real 3D universe. But guess what? There's another universe here that is parallel to ours. Okay? And it exists in this imaginary space, okay, using imaginary arithmetic and algebra. But you see, the energy is negative. And you also notice that you can have positive infinite energy, and you can also have negative infinite negative energy. Okay? So it moves in both directions here. Okay, the characteristics of Dirac 3D space. Well, we all know what they are. Okay, you have positive energy, positive mass, time is forward, you have positive temperature, negative space-time curvature is, of course, what Einstein worked out with his general relativity. Gravity is attractive. Okay, the characteristics of Dirac imaginary 3D space. Okay, it's at right angles to our universe, to our real 3D universe. Imaginary space is at right angles. We have negative energy, negative mass, time is reversed. They call that phase conjugation, okay? Where you have two waves moving in opposite direction. One is a time forward wave, the other wave is a time reversed wave. So you have symmetry. You also have negative temperature and what we call a positive space-time curvature. And this is what I'll get into in my next lecture with Tom Vallone's group on Saturday. I believe that lecture will be given Saturday at 1 p.m., where I'm going to talk about practical warp drive technology. And believe it or not, we had warp drive since the 1920s. So I'm going to get into that information on Saturday. Okay, so you have a positive space-time curvature. Gravity is repulsive in this complex domain here, this imaginary 3D space. Okay, so what is this Dirac hyperspace model all about? You have real space, shown over here, real 3D space. time in the middle here, where time can move forward, but only for a real 3D space, and then time reversed for imaginary space. So we have what? 7 dimensions. We're in a 7-dimensional universe, and it's described perfectly by this Dirac equation. Okay, so we have positive energy on one side, negative on the other. Einstein in his general relativity is really only 4, he describes 4 or 3.5 dimensions. So it only describes negative space-time curvature in real 3D space and a half a dimension of time, which is the time forward component. That's your general relativity. Well, what about the rest of this here? Well, general relativity is going to have to be expanded to include complex space, the Dirac model. So then you'll have a full 7-dimensional general relativity to describe our universe. So, just to finish up here, the Dirac hyperspace, of course, Star Trek calls it subspace, all right? Dirac hyperspace, 7 dimensions. We're working with 7 dimensions here. All right, the electron. You know, I've done a lot of calculations here, and I discovered that the electron is empty. It's just a spinning vortex of energy. That's all the electron is. But it's completely empty on the inside. There's no electric field. There's no magnetic field. All those fields are on the outside, including the mass of the electron. The mass is in the field of the electron. So we have, when you do the calculations, you discover the electron has no volume. Because what quantum physicists want to do is to assign electron, give it a mass, okay? Give it this mass, an internal mass. But there's no mass there to put in there because you have no volume. You only have a radius of that electron. You have a surface area, but there's no volume. So it tells me that there's nothing inside the electron. It's just a spinning vortex of electric, magnetic, and this angular momentum. Those are the 3 components that make up an electron. And so with this mass component, you have this energy-mass relationship, and it's contained in its angular momentum. Okay, so E equals plus or minus mc squared. That's contained in the angular momentum and of the electron. So, going on to the next step here, the electron can rotate, and this is known, you know, in physics here, that it can rotate 720 degrees. So 360 in our real 3D space, another 360 degrees in its complex space. So that's where the imaginary dimensions fall into place here. The Dirac universe only consists of these 4 particles, and it really comes down to 1. There's really only 1 particle that makes up everything in the Dirac universe. And that, of course, is this electron. And you also it's also paired with the positron, which was predicted by Dirac. You had the positron, electrons and positrons. The charge on the electron, the negative charge is a time-forward charge. The positive charge on the positron is time-reversed. It's a time-reversed charge. And that's why Feynman and Stuckelberg came along in the 50s and said that, gee, you know, the positron is a time-reversed particle. Well, they're partially correct. Okay, they're partially correct with that. You have to factor in the angular momentum in this to have a real 3D particle, because that angular momentum can only exist in real 3D space. But then if you torque the angular momentum, you can torque it into these complex, this complex domain. And that's what we're doing with our technology. is that we're supplying a torque to the angular momentum. And that angular momentum can be attached to either the electric or the magnetic field of the electron, or both. So you have these four fundamental particles. One is a spin up, the other one's a spin down. You have the magnetic field component here, and the electron, positron is your polarization of these particles that make up the ether. So Hodson talks about an electromagnetic ether, brought forward by Lorentz, reintroduces that concept. And so you have electric fields and magnetic fields that we're working with here. And then this counterpart, and the negative energy version of this, is where you torque the angular momentum. Just a little spinning particle, a little spinning engine are these electrons and positrons. But if you torque this angular momentum, you can get that mass to flip. Okay, you can get this electron mass, which is in this angular momentum. You can torque that and cause the mass to go negative. Okay, and that's what we're doing with our technology here. So this is the counter version of each particle. So you have spin up and spin down of each electron and positron. And of course, the negative mass version can only exist in imaginary 3D space. Now you can have in-between versions of this too, where the electron exists in both space. Okay, so I worked on this equation and made a number of very interesting discoveries. It's the Biot-Savart law. And believe it or not, the Biot-Savart law incorporates special relativity. Now, some of that comes out of William Hooper's work. If you examine William Hooper, he attached Einstein's special relativity, the gamma, to the electric and magnetic fields. Well, I found out in my work that the Biot-Savart law, which is the magnetic component of the electron, moving, let's say, through a wire, produces this magnetic field, has built into it special relativity. And that, of course, means that the faster the electron is moving through this wire, the greater the field. It's tied right to special relativity. So the mass of that electron increases. The B field, the magnetic field component, increases. So there you have a tie-in with special relativity and with the Biot-Savart law. And then back here you have, the two equations on the bottom represent the Biot-Savart law, the two versions of it. Okay, so when I started working out the math, you cannot put a mass inside of the electron. It just doesn't work. It's in the field. The mass is in the field of this electron. And so when you factor in the mass, and when I worked out the equations, you see that this component over here is the solution of the Biot-Savart law, but it's a relativistic solution. Because what we see here is V squared over C squared. And that's what you see in the gamma of special relativity. And so I expanded that out in this equation here. I did a derivation of special relativity based on these terms as a series of numbers. And so I related this mass increase, to the Biot-Savart law. And then I computed the mass of the electron, and it was almost perfect within, let's say, 5 or 6 decimal points. So I knew I was on the right track here. okay, with this. So we have the Biot-Savart law, where the mass is on the outside of the electron, because quantum physicists want to fill the electron with the mass, but you just can't do it. It just doesn't work. Okay, so we have the mass of the electron on the outside in the field of this electron. And so are the, and of course the magnetic field. There is no magnetic field inside the electron or an electric field. It's all on the outside. And there's this theory going around, and I think Nassim Haramein kind of specializes this, and that the theory, when you go down to the Planck scale, the Planck length, for example, he calls that a Planck sphere. So you have these little spheres of Planck particles at that level, and they carry a charge with them. That charge can either be time forward, carry a negative charge, or time reverse, carrying a positive charge. And that's what electrons, the outer shell of this thing, are constructed of. Okay, so continuing on with this, this of course is the this relativistic solution here, the Biot-Savart law. And then I solved for the velocity of the electron moving through that wire. And so I found out that the energy in that field around the electron, that energy can be either increased or decreased. And the way that you decrease the energy of those electrons is by setting up this opposing field action. Will decrease the energy in that field. And when that happens, the velocity of that electron, it literally vanishes from real 3D space. In other words, the velocity becomes a complex number or an imaginary number. And the velocity, and it's no longer moving through real space at all. It's moving through complex space, which is parallel to ours. But if the energy of that field is increasing, because if you put magnets in the attractive configuration, adds to the field energy. Opposing subtracts the energy, okay? Additive, attractive, increases the field energy, and so that electron is moving through real space. Then it's a real number. And so all our technology here is all positive energy. You're increasing the energy of those electrons. So we're only working with positive energy electrons. But here when you set up this opposing action, you're decreasing the energy of that electron. Electron's no longer moving in real 3D space. It now becomes a complex particle. And so you can model, okay, a little solenoid as a magnet, okay, where I show the increasing or decreasing energy, and then how that relates to the velocity or the motion of the electron through that wire. Okay, measuring Dirac hyperspace. First of all, you cannot measure something in complex space. Our instruments only measure electron motion in real 3D space. So what you're going to be looking at, okay, is a current flow in a wire, okay, that where the magnetic component, the real magnetic field, vanishes. And we do this demonstration. If you want to look at what's really going on there, when you put these magnets in the opposing configuration, the real field vanishes, okay? So these electrons are no longer moving in real 3D space. So it's moving in this complex space. You can't measure that. We can only measure things moving in real 3D space. Okay, so we got a patent. What I'm telling you today is in a patent that I filed last week, and that's what I put my presentation together on. The information in our patent is what I'm presenting to you today. Okay, so it was filed last week. And it's transformers utilizing complex magnetic fields, okay, produced by conditioned permanent magnets. You can go to Lowe's, or Home Depot today, buy a set of ceramic magnets, set them up in their opposing field action, and see the effect for yourself. There's a little bit of negative energy there. Okay, you can apply that to transformers and actually see this effect where the input power drops and the output power remains the same. You're still driving a full load, but with decreased real power being delivered to that transformer. You can actually see that happen. Okay, so positive versus negative energy in electric circuits. Okay, so all our technology is based on this one principle here, where we apply energy to that electron. We're pushing that electron through that circuit. So we're supplying positive energy to move that electron. Okay, whether it's in your laptop, your cell phone, these lights, everything's powered by this positive upper half of this circuit here. But what about the negative energy side of this? Okay, we're not doing anything with that today. It's just as real as what we're doing here with positive energy. But here, you know, I've heard for years this phenomena of cold current. And I kind of pondered that, you know, what is cold current? As opposed to hot current, what we have here. Because if you send hot current through a resistor, it produces divergent heat. It gets hot. But this cold current just does the opposite. That resistor will get cold. So what we're doing here is that we're applying this negative work function. When you set up this opposing field action, you're lowering the energy of this system. Okay? And when you lower that energy, you're not pushing the electron, you're pulling on that electron. Okay? You're taking energy out of the system and you're pulling those electrons as opposed to pushing the electron. So it's just the opposite effect. That's negative energy. And that's what we have defined as cold current, is negative energy. And you apply that negative energy to an inductor, for example. Okay? When you apply negative energy to an inductor, the field, the magnetic field of that inductor becomes a complex number. The real field vanishes, all right? You can no longer measure that real field, but it curled or rotated right into this Dirac hyperspace. The field is still there. It's now a complex field that exists in imaginary space. So what does it do? It does negative work. It's a negative work function, okay? So you have a complex current, okay, flowing through that circuit now. The voltage here remains the same. These can be both 120 volt AC systems, but now the current has been impacted by this negative energy field. Rather than positive energy, we have negative energy here, and a complex current flowing through that circuit, all because of this opposing action that we're putting on this inductor. Okay, so this is our transformer. I call it the complex transformer. And here's our conditioned magnets, top and bottom. And you'll notice a resemblance between this and the Floyd Sweet device, okay, where he used his barium magnets. He conditioned his magnets such that they put out a lot of negative energy. And you do that by pulsing these magnets with high energy. And they retain the magnetization. And here, when we put the magnets together, you have a large amount of negative energy. And that's what we're adding to a transformer. So this transformer consists of a couple of coils, an input, output coil, and then we apply our negative work function here and here. Okay, the magnet conditioning process. This, of course, is where we have two magnets. We force them together. The field that comes out, both faces here, top and bottom. What you see on the internet on a lot of these magnet diagrams, when you show two magnets coming together, that's not the real field they're showing you, okay? This is what's going on here. The real field comes out of the side, the seams between the magnets. That's where the real field comes out and kind of curls around here. But the top and bottom of those magnets are producing a complex magnetic field. And this is what we're interested in right here. And this is what Floyd Sweet did back in the 1980s. He had his conditioned magnets that were putting out a lot of negative energy above and below his coils. Okay, so the complex transformer schematic. Okay, of course we have our top and bottom here of opposing field action produced by these magnets. They're also conditioned to put out more energy. Okay, so you have to pulse these magnets with a high energy magnetic field so that they retain that high energy, and that's what Floyd Sweet did. Here's your coils between those two conditioned magnets. You have power coming in, power going out. Okay, you have your little power source there and your resistive load on the output. So here you have positive energy coming in, positive energy going out, and negative energy coming in, okay, through the top and bottom. Okay, the physics of these transformers. There's really no difference between the complex transformer equations and the traditional transformer. There's no difference other than this right here. We add in the energy, okay, from the magnets, the negative energy. And so when you look at the equation here, the place where you inject this negative energy is that a transformer, when you look it up on the internet, it's an electrical to magnetic to an electrical device. That's all it is. Electric, magnetic, electric device. Where we introduce our negative energy, magnetic field, is in the magnetic field portion of that concept. Okay, that's where we put our negative energy into. And so it shows up as an imaginary number. Okay, that magnetic field. You can no longer measure it. It's there, can't measure it. But it gets added to the input positive energy you're putting into it to magnetize the magnet. That's this L1 max equation, and that's produced by the voltage on Faraday's law. Okay, you have a voltage, you apply it to your coil, and it produces a flux in that transformer. And that flux is you're magnetizing the device. So that's your magnetic energy component there. And then you factor in, you add that to the amount of energy you're driving your load with. Okay, because the input, the power source, has to drive that too. So you add these three components together, and that's the total amount of magnetic energy that's in a transformer. Now there's one stipulation with this. In order to get the fantastic gains, okay, that Floyd Sweet observed, 1,000,000 to 1 efficiency, that's incredible. This magnetic component, it has to be greater than the sum of the energy you're putting into it, the positive energy with the transformer, because that's what you have with the real transformer, positive energy in, positive energy coming out, right? You have a kilowatt coming in, kilowatt going out. But then you add in this negative energy from this field here from the magnets. And that all sums up here. And he discovered that it's the positive energy minus, okay, the energy produced by those magnets. That's part of the equation here. So then you find out that the total real magnetic energy can go to negative. Okay, this magnetic energy can become a negative number. Okay? Okay, so the next set of equations, I looked at the amount of energy. Now keep in mind that all this energy is in the field of the transformer. Okay? That's where all your energy is at. And so you can use this equation of energy equals 1/2 times the inductance, okay, times the current. And you do that for the input and output of the transformer. And then you come to find out here that the input source current vanishes. And this is where Floyd Sweet observed that if he put a milliwatt in, was getting a kilowatt out. Well, where did the kilowatt of input power go? Well, it curled right into hyperspace. That kilowatt is still there, but it comes in the form of negative energy now. And so the real instrumentation you have hooked up, gee, I'm only measuring a milliwatt coming into this thing and a kilowatt coming out. It curled right into Dirac hyperspace as negative energy being supplied by those magnets. Okay, so the current becomes a complex number, turns into cold current on the input of the transformer. Now the output of the transformer, when you follow Faraday's law, okay, is that the flux, you still had the magnetization, positive energy flowing in there. The flux still follows Faraday law on the output of your transformer. So you're going to have the flux inducing a voltage on that output coil, and it's still going to be a real voltage driving a real load. That's where your kilowatt is on the output of this. But your input, okay, is where all this complex business comes in, because the load on your input is the input coil of the transformer. It's an inductive load on the input of your transformer. So this is where the magic, the card trick is in all this. It's on the input side of a transformer, becomes a complex current. You can no longer measure that. So the real current coming out can be almost zero. It depends upon how much energy, negative energy, you're getting out of those magnets. If you get a little bit, then you see a little drop in your input current. And you can do that today. You can just run over to Lowe's and buy a bunch of those magnets and try it out for yourself. You'll see a little drop on the input power, but the output power remains the same. Well, here, when you condition those magnets, you see a huge drop. Okay, a lot of negative energy getting factored in here. So you can get it to the point where that negative energy can offset your positive energy going into the transformer and coming out of the transformer. So you're still driving a real load, you're still driving a kilowatt on the output of this thing. It's real positive energy, but the input has curled right into Dirac hyperspace. So then we see that, okay, the output load current, the load current is real, so that's where you're driving a real load with a kilowatt. So when you go and measure this, you discover this little relationship there, where it says your input current is now less than your load current, okay? Okay, and then we come along, we just measure our power and determine the efficiency of this new transformer being supplied with negative energy. And so we discover in our calculations here, it's like, hey, wait a minute, if my positive energy is offset by this large negative energy component, I can have an efficiency approaching infinity on that transformer. All because of the negative energy coming from those magnets. So you're going to have an efficiency greater than 100%, which is all you can get out of a traditional transformer. You can only get up to less than 100% efficiency. But with the negative energy component added in, and that's all there is, just that negative energy component, now I can have an efficiency of approaching infinity. So that's what this technology does. Okay? The technology, when you add negative energy to your devices, it improves the efficiency of operation. And that can be with plants. You can add negative energy to growing plants. It restructures water because you're taking the energy out of that system. It's negative energy, you're taking it out. Okay? Rather than putting energy in, positive energy in, we're taking energy out with negative energy. Everything starts to operate more efficiently. Okay? So you see better plant growth. It restructures water. It takes the energy right out of the water and declusters the water for nanowater, so you can absorb the water a lot easier. You can absorb the nutrients, water, and it has very beneficial biocompatible effects. You get a lot of EM, a lot of electromagnetic radiation from these electric cars now. A lot of people are driving electric cars. Well, the fields coming out of those cars is just overwhelming. It can overwhelm your body, okay, with those positive energy fields. If we had negative energy into those equations, okay, into those cars, the cars would become much more biocompatible, much more efficient. You see? That's how this works. Okay, so designing free energy over unity devices, we now have a mathematical basis, okay, for understanding how to harness this Dirac sea of negative energy. So we set up electrons in this opposing magnetic configuration, forcing the electron to rotate or curl running into this Dirac hyperspace. So we're changing this energy-mass relationship. And the real electrons vanish from real 3D space, okay, and they show up in this complex space. And there we can work with negative energy. Okay, so the transformer, we can approach infinity. Anything above 100% to infinity is would be the new norm, adding in this negative energy to the transformer. Okay? So with power can become a complex number. You can work with complex powers. So the source power can be almost zero, but you could be driving a massive load, all dependent upon how much negative energy you're putting into that system. So we can see efficiencies can approach infinity with all our existing technology, just by adding in negative energy. Okay, this is how you compute efficiencies, looking at input power, output power, and doing this calculation. Okay, we do demonstrations for people. I can show you the effect. I brought some equipment with me. If you want to see the field, we call this, what we're doing, what all our technology is based on, is of course this negative energy effect. And so we call that a magnetic dampening field effect. It's a magnetic dampening field. Okay? And there's only two places where you hear that terminology. One is Star Trek. They talk about dampening fields in a lot of their episodes. The other place where you hear about a dampening field is with the UFO phenomena. Okay, that when a UFO approaches cars, and you see this in a lot of programs, documentaries, and when a UFO approaches a car, for example, it literally shuts down the car or shuts down a jet engine or instrumentation. When the UFO leaves, everything comes back alive again, okay? That's a dampening field effect. So there's really only two places where you hear about this. And of course, Star Trek was based on reality, okay? But Aurora can tell you more about that. Okay, so check out our product page. We're introducing technology utilizing this negative energy field, this dampening field, with fast growth technology for plants, vitality energy pads, which I think was auctioned off, I'm not sure though, but, or raffled off. Water restructuring. We're going to be coming out with these Overunity transformers, and again, I just got our patent filed. And so we're going to be introducing a line of transformers at various power levels, okay, of supplying negative energy to the circuit. We also talk about anti-gravity, that's based on the Barnett effect, where you can amplify the negative energy field just by rotation. That's called the Barnett effect. So you can have anti-gravity with that, and also warp drive engines. And I'll be talking about that this Saturday. And that's our product line that we're working on. Divisions of Aurora Tech. Okay, we got our biotech here. We got energy and space applications. And of course, that's all based on time reverse negative energy technology. You can invest in our company. You know, we have investment opportunities, currently at $1 a share. So if you want to jump on board with us, you can. Just contact Aurora. We have the answer. Okay, and we're offering deals. We also do a weekly radio show. And if Aurora's absent, I get to go crazy with all my technical talk. So if you can stand it for an hour, just tune in on Monday evenings. And here's our contact info. So that is my presentation. Any questions?
Thank you very much, William Alek. If you have any questions, please come on up.
Bill, can you actually take 3 of these transformers, hook them up in series, and have them run themselves?
What's that again?
Can you take 3 of these transformers and hook them up primary to secondary in a loop and have them run themselves after you give them a start pulse?
Well, keep in mind, all that we're doing is adding in negative energy into the transformer, improving its efficiency
Right.
of operation. I mean, yeah, you can stack them together, okay? But does that improve the efficiency of the transformer?
No,
Well,
I'm
that's a
asking
good
if the
question.
Overunity transformers in the real world, putting out real power, can they run themselves in a loop, a closed loop?
Oh, closed loop.
Yeah.
Yeah, that's what we're working on here.
Okay.
You see, what Floyd Sweet did is that he had, I believe he was just using a, one of these little alternating wave function generators. And here he was driving a kilowatt load with it. His
Yeah, I read his
transformers.
work.
And all the power was really coming from his magnets, okay, the negative energy, offsetting the positive energy that you're putting in.
And my second question is, you said it shows up readily. So apparently, if you move a current down a conductor, by using opposing fields, I work with magnets a lot, and by using opposing fields, you get one effect. By using no fields, a second effect, and by using attractive fields, you get a third effect. One adds to the...
one adds, the other
one subtracts, and one is neutral. So how do those show up in numbers? How do you actually measure that? What do you measure when you measure that difference?
Well, our instrumentation can only measure, real current, real voltage, real power, okay? But once things start to curl into this hyperspace, then you start looking for effects, okay? One effect would be, gee, this resistor is not running hot. I observed that phenomena occurring with this transformer that we have for our first patent, okay, what I call the split flux transformer that has these 3 cores. And I observed that, here I am driving 20 watts with this thing, and yet it barely gets warm. And that's all because we're canceling out this magnetic field component, okay? And, we're getting some of this negative energy function coming into your circuit. So it's just not going to run as hot as it would with a traditional transformer.
I see. Okay.
I mean, the load still runs hot.
Right.
Okay, you're still dissipating 20 watts, right?
Sure. Putting out whatever torque you're putting out, yeah. And my third question is, how did you eliminate inductive reactants as a consideration when you were conditioning these magnets to put on the ends of the coils? Because obviously when you pulse them, they're conductors. Obviously you're going to get inductance in it, and you know how that works.
Okay, well, when you look at the transformer, there's
Pardon?
2 loads.
I'm talking about the magnet.
Okay.
Now, you condition those magnets by pulsing them.
Right.
Okay. Now, when you pulse them, of course, you're pulsing a conductor because currently we believe that it's currents circulating within.
Well, it's going to retain that excess magnetization.
In the form of inductive reactants.
Well, you're going to pulse it with a high energy magnetic field.
Right.
Okay. And so it's going to retain that excess magnetization. So that when you put these magnets together,
right,
you're going to get a large negative energy field coming out.
Right. No, I'm sure I know how they work, how they reflect through materials. I'm really intimate with that. I'm just saying, but as a consideration and as in opposition to pulling in things from the environment or the ZPE energy, how can you be sure that you're not actually inducing an inductive reactance in these magnets that reflects back into the real power?
Okay.
On this source.
When you have inductive loads or capacitive loads, you have this phase shift that occurs between, okay, it actually occurs in the ether there, where you have your electric field, okay, your electron-positron pairs, it's right along the axis, the electric component. It's right along the axis of your electron-positron pair. You have positive and negative. Now, each electron and positron has a magnetic field associated with that fundamental particle. So what we're looking at is a phase shift that occurs between the electric and magnetic components. Okay. Now, the phase shift that I'm talking about is a phase shift that occurs when we're transporting, and I'm going to get into this Saturday with the ether, the electromagnetic ether, a phase shift that occurs because you're transporting, a photon is, according to Hodson, when you really look into his work, you discover that a photon, it's neither a particle nor a wave. It's neither one of those. It's angular momentum that's being transported along a polarized chain of electron-positron pairs. Okay, it's transporting the energy, okay, along these chains. It polarizes the random fluctuations you hear about. Okay, it polarizes those into chains, going from a positive to a negative particle, or a negative to a particle, negative to a positive particle. There's real energy being transported there. And that's according to the energy-mass relationship. So you can really say, well, there's mass flowing in there at the speed of light because these electron-positron pairs have to dump that energy okay, along that chain. And then when you start to look at these fields, that when you start to compress those fields, okay, those chains, those flux chains, is where you start to torque that angular momentum. And that it has nowhere to go but into complex space, okay? So the real field component vanishes. And so you have this complex number to work with, complex angular momentum. You square an imaginary angular momentum, and what do you get? You get negative energy, okay? Just the way all the equations, they all work. Even though you're working with negative energy, complex space, all the equations still work perfectly, all right? Just that we add in this complex space, all of a sudden you can do this stuff. So, looking at your question there, yeah, you're going to pulse these magnets with high energy, increase its magnetization, so you can increase this negative energy effect. And this is what Floyd Sweet did with his magnets, because he would imprint north-north, south-south, north-north, south-south, and bed them, reprogram his magnets such that they would put out this large negative energy field. And that just gets added in right into the equation as negative energy into the magnetic portion of that transformer. So all the math still works when you go and calculate, okay, all the energy and power and this and that. Just find out that, well, some of this stuff is in complex space, represented as a complex number. Next question.
You made a reference to extremely high efficiencies.
Right.
Does that have a corollary with extremely low temperatures? Because I used to work with Walter Rosenthal, and he worked very intimately with Floyd Sweet.
Mm-hmm.
And I remember him telling me that on various occasions he would ice over his magnets and they would split. So I'd imagine if you go to ever-increasing efficiencies, you would approach, if you approach affinity on one side, you would probably approach absolute zero with the energy, with the negative energy.
Mm-hmm.
So you'd have to...
Yeah, when he shorted the output of his transformers, ice would form on the wires.
Right.
Okay, that's your cold current. And that's all being delivered by the magnets. That negative energy from the magnets is offsetting the positive energy you're putting in.
All right.
Okay, so you have cold current, but it's only flowing on the input side. You're only going to see cold current on the input of that transformer.
Right. That's right.
The output is still driving a real load.
Right,
okay?
exactly.
All because of Faraday, because you're setting up voltage to flux, back to voltage again.
Yeah, you hear that often whenever you approach Overunity. In that sense, you start getting cold.
But where the magnetic field of the output contributes to this equation is your output current that's driving a load. It's going to be a real output current that's going to show up on your input as positive magnetic input energy that the supply has to supply. Okay? So you have to magnetize the coil, and then you have to supply the output current. That all has to be offset by the amount of negative energy you're putting in from the magnets. So as long as that's super strong, you can offset that positive energy and drive your efficiency way up.
Right.
Now you can have a weak field, okay, coming from those magnets, so you only see a little drop on the input current. But if you want to see a larger drop, you just increase your negative energy input.
Right. All right, thank you.
Ceramic magnets are pretty weak.
Mm-hmm.
Is there a substantial increase in the effect if you use rare earth magnets?
Well, the work that I've done in the field, I see a much larger negative energy effect with ceramic ferrite magnets as opposed to neodymiums.
As opposed to?
Neodymium magnets,
Okay.
when you force these neodymiums, even though you have a very powerful B field there, okay, the negative energy is pretty well trapped within the zone where you're forcing these magnets together. So you're going to see a little bit more positive energy, but it's still a complex field. Okay, you still have some positive energy and then some negative energy there too, because you're decreasing the energy of that magnet when you force them together like that. It's going to be a complex number where you have real and then imaginary. Okay, and your imaginary component is your negative energy component.
Okay, the magnetics...
But anyway, the field is much greater in a ceramic magnet. That's what I've been noticing. That's why I said, well, you can run over to Lowe's and just buy them right off the shelf, put them together and see the actual effect occur.
We'll call them magnetic sandwiches, top and bottom. Are they both the same polarity? Negatives in north, north,
yeah, well,
north,
you can
north.
stack them. I haven't seen an incredible effect if you just have, a couple of big ones put together or you stack them. It's pretty much the same type of effect. But I like working with the larger disc magnets, like what we filed there.
Okay, and you talked about pulsing the magnets. Are you really talking about pulsing the core or the windings that are around the core?
No, just the magnets, because you want to increase the negative energy output of those magnets.
So you put a separate winding just around the magnets then?
Yeah, right now I'm developing a piece of equipment that's going to deliver a few hundred joules, okay, to a little ceramic magnet. I'm going to punch that magnet. And this is what Floyd Sweet had, in his conditioning system, is that he would punch a magnet. Okay, he had this large cylinder device, and he put his bar magnets or his block magnets on top, and then reprogram those magnets.
Is there some place to find information on do-it-yourself for experimental purposes?
Well, that's what I'm doing. Yeah, just search the internet. All the equations are there. I put together all the physics. If you want, I have my patents, 3 patents. You can purchase those. All the information's there.
Okay. Thank you.
Yeah, just come by the booth. I have Dirac's Sea of Negative Energy article there, plus a listing of our patents that you can look at.
Yeah, my question relates to the real and the imaginary.
Mm-hmm.
You talked about 7 dimensions.
About what?
You talked about 7 dimensions.
Right.
Elizabeth Rauscher took Maxwell's equations and for each of the variables let them to be complex. So they had a real part and an imaginary part.
Right.
And in her world, the number of dimensions is 8. Is there anything you can say about the comparison between your 7 and her 8? And by the way, in her 8, you also have the 720 degrees.
Okay. Well, maybe they're doing something with time. I'm not sure. I haven't
She
looked
has
at
an
those
imaginary
equations.
component on time.
But you got real 3D space here, 3D space in the complex world, okay? And then you have a full dimension of time, which includes both time forward and time reversed. And to me, that's 7 dimensions, unless they consider that an 8th. I'm not sure. Time forward. They separate time forward from time reversed, if they're doing that. But I look at it as 7 dimensions.
Thank you.
Any further questions? Any further questions? Thank you very much. Bill Alek. Bill Alek has a booth out in the...